Alright, let's see the Nernst equation in action with an actual example. Don't bother writing all these steps, we'll learn by doing. So here's our cell. It looks like the other ones we've seen. In fact, we've seen this half cell before, copper, copper 2+, and sulfate. But this time we're not at standard state. We are at 0.0100 molar. We have the same concentration of KCl on the other side. This is a new half cell. This time our electrode is not just one metal, but it's a metal with another solid pasted on top of it. So AgCl solid, phase boundary Ag solid. Even though they're both solids, they are clearly distinct, and thus we put the phase boundary. Here in solution we have K plus and Cl minus. The Cl minus we'll see as part of the reaction. The K plus is just the spectator. So our goal for this example is to figure out what is the overall voltage of the cell at these concentrations, and in so doing also learn what is the cathode and anode, what is the overall reaction. So step 1, we write the reduction half reactions for both half cells and look up their standard state voltages. So step 1, on the right side, we have the following reduction half reaction. AgCl solid meets one electron and forms an equilibrium with Ag solid plus Cl minus, which is aqueous, but we won't write that phase. You might be wondering, how did I know that's the reaction? We will definitely get into that later. For now, just trust me. If we look up the standard state voltage of that, we would get positive 0.222 volts. And let's put a little plus subscript to show that this goes with the positive terminal. It's on the right side. Now we're going to write another reaction underneath this one momentarily, so for now leave some space there. But first, let's write what's going on the left side. And we've seen this before. The reduction reaction over there is copper 2+ meets 2 electrons and forms an equilibrium with copper solid. And its standard state voltage is equal to 0.339. 0.339 volts, and let's put a little negative subscript since it's on the negative wire. Now notice this little note here. We have to multiply the half reactions as needed to obtain equal numbers of electrons, which we don't have right now. 2 electrons, 1 electron. So we're going to multiply that first reaction by 2. That's why we left some space. And we get 2 AgCl solid plus 2 electrons forms 2 Ag solid plus 2 chloride ions. But we do not change the voltages. Your instinct might be to multiply by 2, but you don't. Think about why that might be. Why don't we actually double the voltage even though we've doubled all the species in the reaction? I'll give you a hint. Think about what units voltage actually stands for. Another question to ask yourself, which of these electrodes is the cathode if we were at standard state? And you should be able to figure that out rather quickly. It's the copper electrode hooked up to the negative terminal. More positive voltage. But we're not at standard state, so let's see if that's still actually the cathode. Step 2. Write the Nernst equation for the right half cell. So step 2, we are looking for the actual voltage of the right half cell, in other words, the one hooked up to the positive terminal. And so we set this equal to the standard state voltage on that positive wire, which we've already written down. It's 0.222. And then we have this modifier we're going to subtract from it. 0.05916, which we saw before. In this case, the number of electrons in the reaction is 2 after we did that multiplication. Then we have log. And then, well, for the Q expression, we just have to look at our reaction. We have a solid product, so that's not going to go in. We have an aqueous product, so that will go in to the second power. And over here, we just have a solid reactant. And we don't worry about those electrons. Those are taken care of here. So all we wind up having for Q is the chloride concentration squared. And we get that concentration from the figure above, 0.0100. From here we just plug everything in, and you should get 0.340, and then little 3 since the problem's not even close to being done. That is the true voltage on the right-hand side with respect to the reduction point of view. Now let's see step 3. You can probably guess what this is. And it's write the Nernst equation for the left half cell. So let's do it. Step 3. The true voltage on the negative terminal equals whatever that voltage would be at standard state minus 0.05916 divided by 2, just like before, log. And for this half reaction, our only product is a solid, and our reactant is an aqueous species, but notice there is no coefficient, so there will be no exponent. So since there's no chemical going in the numerator, we just put a 1, and for the denominator, we have copper 2 plus concentration, which we can also get from the figure as also being 0.0100. Solve, and we get 0.279 little 8. 0.279 little 8 volts. And so these are the true reduction potentials for this cell at these concentrations. So which of these is actually the cathode based on the correct voltages? And the answer is the cathode is actually hooked up to the positive wire and the anode to the negative. And with that information, we can do step 4. Judge which is the cathode and write the balanced net cell reaction. So let me make some room by erasing all this. Okay, step 4. Some of this you've already written, but we're just going to write it again. For the net cell reaction, we're going to take that cathode reaction and let's just keep it as is. That was 2AgCl, solid, because we did identify that the positive terminal is hooked up to the cathode, plus 2 electrons in equilibrium with 2 silver solids plus 2 chloride ions. But we now know that the other side is going to be oxidized, and so we rewrite that reaction backwards. Copper solid is in equilibrium with copper 2 plus and 2 electrons. And so if I were to add these two reactions together, I would get 2 AgCl solids plus a copper solid, but we're not going to write those 2 electrons because we can see that those will cancel. So we have those as our reactants, and they are in equilibrium with 2 Ag solid plus copper 2 plus 2 chloride ions. And at these concentrations, this reaction will proceed in the forward direction spontaneously. So spontaneously forward. It is energetically favorable for the reaction to go as written, towards the forward direction. Finally, step 5, just find the voltage difference. After everything we've just done, this step is a piece of cake. The true voltage difference between the two sides, in other words, E positive minus E negative. This difference is just what the voltmeter measures. But notice we've abandoned the standard state symbols because we're going to plug in the actual voltages, which were 0.340 little 3 minus 0.279 little 8. Solve, and then we'll finally deal with sig figs. We get 0.061 volts. Positive value, energetically favorable. So that's as involved as a Nernst equation example gets. Usually I'll actually just ask you about a piece of the process, but you should be ready for any part of what we just went through. After this comes a clicker, and we'll do it in quote-unquote class.